All right, we can start. I'm sure more people will filter in. Maybe, maybe not. It's up to you. Up to you.
No, it's fine. It's kind of like split into two sides.
Okay. Questions about last class? Okay. So there was one mistake in the lecture, and I apologize. Someone actually pointed it out, but I didn't understand what they were saying, which is I missed some brackets. But I'll get to it in a second when we get there. So again, I just pre-populated the notes, so we'll be able to go through it a little bit faster, but it'll be harder to take notes. Okay, so here's the circuit that we've seen already. Here's the layout of the circuit. So we have the circuit trace, we have the selectors for the addition gates, the selectors for the multiplication gates, and then last class we introduced two vectors that will help us denote the permutation meaning the Y rate. And so a way of seeing it too, it wasn't exactly how I drew it last time, but if you actually put them side by side or above each other, you can see that when the numbers are the same, that means that there's no wire. And if the numbers are different, then that means there's a wire between those two parts. So between 2 and 11, so like 2 and 11, there's a wire there. And so it also, so basically anywhere there's an arrow, it means that the values in C in those positions should have the same value, which we call a copy constraint. They should be copied the same. Okay, so how do we prove it? How do we prove that, that everywhere these values are different, they contain the same values? So what we do is we take this, and we sort of sandwich them together. And then we take this, and sandwich them together. And if they're just permutations of each other, then they have the same, the copy constraints are done correctly. And if they're not, then they don't have it. Okay? So the sandwiching step is this. It's also known as a random linear combination. But essentially we set the elements as coefficients in a new polynomial. We pick some random point on that polynomial, and we say that represents the compression or hash or encoding of these two values into a single value. So we do it with sigma 1 in C, we do it with sigma 2 in C. So that gives us sigma 1 and sigma 2 tilde. Then what we want to do is we want to prove that these two are set equal. So what we do is we take the values and we kind of program them into a new polynomial. This time we set all the values in these arrays as the roots of the polynomial. Okay, and so the format for the roots of the polynomial is the variable minus the root, all multiplied together. All right, so we set this up, and then we feed it into something that will take the product of them. And if they're the same polynomial, they'll have the same product. And so if we have a way of proving that these two things have the same products, then we're done. Okay? So again, we pick a random point, in this case gamma, and we evaluate both of these polynomials at that point. And we say that if they're the same at that point, then the polynomials are the same. And if they're the same polynomials, then they're set equal. Okay? So the value here on the wire right before we go into the same product is, here I use sigma again, but this time it's a hat as opposed to a tilde. So just hopefully that doesn't confuse you. We'll actually not use this tilde. It's just kind of an intermediate value. So you won't see it again today. But anyway, so sigma hat is going to be gamma minus, and then I forgot the brackets last class, so this is the correction. There should be brackets here, and it's going to be sigma 1 tilde. Sigma 1 tilde is equal to sigma 1 plus beta c, so that's why I have here sigma 1 plus beta c. Okay, so in other words, we're going to compute this you can think of as a vector of values, and we're going to compute this as a vector of values, and then we're going to prove that the product between the two are the same. Okay, so questions about any of this before we talk about how to prove that they have the same product? Okay. All right, so first thing I'm going to do is I'm just going to compute these values sort of graphically so you can see them. So let's assume that the verifier chooses beta 57 and gamma equals 17. So these are the 2 points that they choose. Then in that case, gamma is always 17. So you can think of it as kind of like a vector of all 17. Beta is always 57. So you can think of it as a vector of 17. Sigma 1 is 1, 2, 3, 4, 5, 6 to 15. And then C is our circuit trace, okay? And so it's 17 minus 1 plus 3 times 57. And that, if you worked it out, that would give you 28 mod Q. So remember, we're always working mod Q. Okay, so similarly here, 17 minus 2 plus 57 times 5 gives you 35, and then likewise you can work through it, okay? So constructing this value is easy. It's just you have 2 vectors, sigma and C, and you have 2 constants, gamma and beta, and so this is the value, okay? And then we can similarly do it for sigma 2. Okay, questions about that step? Okay. Now, the question we want to prove, what we want to prove is that this array and this array have the same product, okay? Do they have the same product from inspection? And why?
Because they have each member of one is equal to one.
Okay, so these are already, you can see they're already set equal, okay? So yeah, there are permutations of each other or whatever, okay? So anything that's set equal will have the same product, which is something we saw last class as well. So these are going to end up having the same product. That product happens to be 25 if you work it out. But in Plonk, you're never going to reveal that value, the 25, okay? You're just going to prove that they have the same value. Whatever that value is, it's not going to be disclosed. Okay, so this is what we want to prove. We want to prove that if I sum up all the elements of sigma 1, x, where x is all the values of the domain, and I compare it to, sorry, I said sum, but I meant product. I compare it to the product of all the values of this at x. So I'm thinking of these as polynomials now over the domain. I should get the same response. Or same answer back. Okay, so the product of this equals the product of this. Okay, so I'm going to do a little bit of rearranging, and then then there's going to be like the hard step, and then everything else will be just sort of rearranging and things like that. Okay, so first, just to rearrange this, what I'm going to do is I'm going to say that if I move this over to the other side, I move this over to the other side and divide it, then this will equal 1, okay? So imagine all of these being multiplied to each other, all of these being multiplied to each other, okay? It's going to equal 1 because they're all going to cancel out, right? So there's a 28 on top, there's a 28 on the bottom, there's a 35 on top, there'll be a 35 somewhere on the bottom that will cancel out. And so as long as these are set equal, right, then obviously they're all going to cancel out. And similarly, if they all cancel out, actually, I guess this isn't true. I'm gonna remove the if and only if. I'll keep it as an if. Okay, so if they're set equal, everything will cancel out. If they're not set equal, probably it's not going to cancel out, but there is, I guess, a chance that it would cancel out just because like two of these numbers would happen to multiply together to give the same number. Okay, it's very unlikely, so that the only if is very, very unlikely. The reason it's unlikely is because we choose gamma here randomly, and so you would have to get really lucky with a nice value of gamma so that this equation would hold if they're not set equal. Okay. So why don't I write here and overwhelmingly only if they're set equal. Okay, now, what does it mean to divide? Can I divide? So remember, everything we're doing is mod P, or mod Q, okay? So I don't have division, but what I have is the inverse, and so I can multiply an inverse, okay? So when I say 28 divided by 28, what I'm thinking is 28 times the inverse of 28 mod Q. 35 divided by 26 is like 35 times 26. The inverse of 26, 46 times the 42, the inverse of 42 mod Q. Every number has an inverse. That's one of the number theory properties that we saw like a long, long time ago at the start of the semester. Okay, so if I were to do this, I would end up with this array, okay? And so now what I'm asking is, if I multiply all of these numbers together, mod Q, is that going to give me 1? Okay. If it gives me 1, then these two things have to be set equal. Okay. And if it gives me something other than 1, then there was something here that didn't cancel, right? And so they weren't set equal. Okay. So I've reduced this sort of problem of, is the product of this equal to the product of this, to does the product of this equal 1? Okay. All right, now here's the hard part. How am I going to prove this? Okay, so I want to prove that the product of this vector equals 1. And as always, I need my proof to be succinct. So I can't have a proof where I'm, like, say, opening 15 values or something like that, because this array could be very, very long. Okay, so I need it to be succinct. Okay, now just conceptually, let's say I'm trying to figure out whether this array equals 1 or not. Do I have to look at the number 42 to know whether that's true or not? So I do. Okay, I need to look at the number 42. If 42 was a 43, would it be true anymore? So it would get compressed to a 1, but just at a high level, I need to I need to look at this number 42. I can't decide whether the product of everything is going to equal 1 without looking at this particular value, right? If it was a 41 or a 43, then it wouldn't or wouldn't be true. And you can say the same thing about this value 1, and you can say the same thing about this value 60. In other words, what I have to do is I have to look at every value in the array to decide whether this equals 1 or not. Okay? So it's going to be really hard to give a proof that the product of all of these equals 1 if the proof depends on every single value in the array. Okay, if it depends on every value in the array, I'm going to have a hard time making it succinct, okay, to give you some like small bite-sized proof that depends on the entire array, okay? So the trick I'm going to use, and this is used a lot in SNARKs, not just in Plonk, but like elsewhere, is what I'm going to do is I'm going to build a helper vector called an accumulator, okay? And the idea of accumulator is actually pretty simple. what I'm going to do is I'm going to have a new array, and the first one I'm going to have, say, a 1, okay? In the second element, I'm going to have 1 times 60. Then in the next element, I'll have 1 times 60 times 4, and then I'll have 1 times 60 times 4 times 1. So you can think of it as kind of like a running product. Okay, so it's going to have the running product of this particular, wherever I'm at, and all of the previous values itself. Okay, why is this any better? Don't know yet. Okay, but just suspend your disbelief. Let's try and understand the construction itself. Okay, so this is how I'm going to build it. There's different ways of doing it. This might not be the most intuitive way, but it doesn't really matter how you do it as long as the math is consistent with how you do it. What I'm going to do is I'm going to start by dropping the value 1 in my accumulator. Okay. Then the next value is going to be the product of basically the running product up to the value right before it. So it's going to be the running product up to 1. The next value will be the running product from the first 2 values. The next part of my accumulator will be the running product of the first 3. So 1 times 60 times 4. Okay? And then the next one will be 1 times 60 times 4 times 1. And then that times 1. And then that times 31 will give me 59. And I'll keep building it that way. Okay?
Is there a Q of 97 again?
Yeah, sorry. So Q61. Yeah. K is the number of elements that we have. So we have 15. So that's the order or the degree of the, well, it's related to the degree, or it's the order of the root of unity. It's the kth root of unity. And then 22 is the root of unity. So those are the 3 sort of parameters. Yeah. Okay, so I'm going to build this accumulator. All right. Now, let's say the product of this is actually 1. What's the last value in my accumulator going to be? It's going to be 1. Okay, so the last value in my accumulator will be the accumulation of the entire vector. Okay, I'll have I have a running tally now of the whole vector, and so that will be in the last vector. Okay, now we have a slight problem here, which is because I started at 1, I'll tell you why I start at 1 in a second. My accumulator is bigger than my product here. Okay, so I have this dummy element 1 here, then I have all the values in my accumulator, which equal 1 in the end. I'm going to make this pink just because it is kind of like a secret value, so I've been using pink as sort of secret values. Okay, but because we're using roots of unity and things wrap around, we're going to fix that problem. Okay, so we're going to be able to fix that problem without making this 1 bigger. Okay, all right, so first what I'm going to do is I'm just going to draw in what's going on. Okay, so what I'm doing is I'm taking this value here, what is it? Well, this value is going to be the product of this value and all the values before it. Okay? Where are all of the values before it? Well, that's what's in the previous value here. Okay? So this is all the values before it. So this is this value times this value. Okay? Let me draw it in the middle. I think it's hard sometimes. The start and the end is hard. We call them the boundary conditions. It's maybe a little easier to see in the middle. Okay? So this number 45, where did it come from? 45 is 1 times 60 times 4 times 1 times 1 times 31 times 46 times 32. Okay? So 45 is the running product up to this value here. Okay? All right. If I want to compute the number 45, do I have to look at all of these values here?
Just look at 30 now.
Exactly, yeah.
It's the running product of the previous values.
Perfect, perfect. Okay, so to understand that, if I want to compute this, what I can do is I can compute 32 by 30, because 30 is already all the stuff in yellow, okay? So the running tally up to 46 is already sitting here. So all I have to do is I have to take the next value, right? And I have to multiply it by the running tally, and then I get 45, okay? Okay, why is this useful? Okay, so the reason why this is useful is before here, I had a problem where in order to tell you whether this is 1 or not, I had to consider every value in the vector, okay? Here what I do is I have a rule, and the rule is local in the sense that the value in here, it only depends on 2 other values. It depends on this value, and it depends on this value, okay? So I can prove to you that the 45 is right by only considering 2 other values. And that's true of the entire vector, okay? Maybe with the exception of the boundary conditions, which we have to work through, okay? So I took a rule that is about the whole vector, I made it like a smaller local rule, where you only have to reference 2 other things, okay? And what I can do is I can apply that rule to all the elements of the vector at the same time, all right? Okay, questions about this? I'm just going to draw this a little better because it was kind of not drawn very well.
So we're still in the proving phase, right?
Yeah. So this is a temporary vector that the prover's making. All these pink values the verifier doesn't know. And so the prover is going to give a commitment to this to the verifier. And then then they're going to have to prove that they applied this rule correctly across the whole thing. Okay, questions about this? Okay, now let's consider the boundary conditions. Okay, what happens at the start and what happens at the end? Okay, so what happens at the end, the way I've drawn it for now, is we have this sort of extra element here. Okay, and if this ends up being a 1, that means the product of this whole thing is a 1. Okay, so that's fine, that's right, but we're going to have to check that this is 1. But right now it's kind of awkward because this is bigger than this, so I need to put this somewhere. Okay, the other boundary condition is what happens on the first element. Okay, where does the first element come from? Okay. The first element comes from, well, the previous 2 elements, right? So it's going to be the product of the previous element. There is no previous element, okay? Now, because we're using roots of unity, what that means is that these things wrap around, okay? So the previous element will actually be, it will be the last element of the other thing, okay? Of the other array, all right? So what we can do is, what we'll end up referencing is we'll reference basically whatever's here. So this will feed into this, which will end up wrapping around to this. Yeah.
You have the first array, but the second one, aren't you using that to build it?
Yeah, so at first I just programmed this with a 1 in order to build this. Okay, why did I program it with a 1? Then we have to consider this one. So this is going to be the running tally of the first element, right? But then I have to reference the element before me, okay? But the element before me, I don't want to change it. Like if this is a 10, I want to have a 10 here. So that's why I put a 1 here so that it doesn't change it.
Always start at 1.
So we always start at 1, yeah? Okay, so what I can do is at the end, because I need to end in 1, right? I'm trying to prove that the product of all of this equals 1. What I can do is I can stick this 1 here. So I'm going to start at 1 and I'm going to end at 1. okay? I'm ending at 1 because I'm having to prove that this whole thing equals 1, okay? And I'm starting at a 1 because I want to program it to start as a 1. So I can use the fact that those two constraints hold, and I can just merge them together, okay? So what I'll do is I don't need this constraint. What I'll do is I'll just move this over here, okay? So in other words, the rule that I'm applying at every cell looks like this. Sorry, this was, I redrew it. Yeah.
Blink this, is it a branch of math, or is it something that Plonk people came up with?
It's a Plonk thing. Accumulators in general, like if you have a running, like say you have a bunch of numbers, and then you have a second array, which is the accumulation of those numbers, that, like a lot of algorithms use that kind of thing before, right? But seeing that it applies in this scenario was very much a Plonk insight.
Like proving multiplication is the first time that it's being done.
Yeah, so so Plonk itself didn't come out of nowhere. So it was based on earlier systems, like there was a system called Halo, and Halo was built on something else. I think Halo had this idea, so Plonk just kind of, I don't know, I don't remember the exact chronology, but it's as new as SNARKs. So like, even if it wasn't Plonk that invented it, it had only been invented a couple years before, and the Plonk people knew to take that technique and apply it here. So yeah, so it is a new thing for zero knowledge in that sense. Yeah. Okay, so the first value of the accumulator will set to 1, and the last element of the accumulator should always be 1, but because it wraps, the first element of the accumulator, okay, is going to be the previous value and multiplied by the last thing, and it's going to always be 1 anyways, okay? So this, basically it all works out. What we need to do is we need to check that the rule was applied correctly, and we need to pop open the first element of the accumulator and make sure there's a 1 sitting there. And if I do those 2 checks, then I'm happy that everything was done correctly. Okay, so what I'm going to do is I'm going to just turn this into polynomials, okay? So basically what I'm saying is the next element in my accumulator, think of a pointer, it's pointing somewhere at current. So that's current. This is sort of next. So my like update rule, actually it might be helpful to think of the boundary first. So I'll program the first element of my accumulator to equal 1, okay? And then for every next value in my accumulator, I'll set it to be the difference, the division of these 2 sigma values, okay, at the current vector, multiplied by the previous, or sorry, at the current value of the accumulator. So the next value of the accumulator will be the current value of the accumulator multiplied by the current value of the division of these 2 vectors here, okay? So it's, so the next element, 45, so in this case, current is here, next is here. So I'm going to take the current value, 32. 32 is it came from the division of these 2 things, okay? So I'm going to take that value, 32. I'm going to multiply it by 30, and I'm going to program that into the next element of the accumulator, okay? So the next element of the accumulator is the current value, the division of these 2, multiplied by the current value I have in my accumulator. Okay. Then I can turn this into polynomials. And so how do we sort of get the next element in a polynomial? Like if I'm looking here and I want to move over 1. Okay, so I'm going to multiply by omega, by the root of unity. So we have it up here. So 58 times omega is 56, 56 times omega is 12, et cetera, et cetera. All right. So the next element is simply omega times the variable. And then the current elements will just be the variables themselves, okay? So this is now is a polynomial. And because we have this relationship of polynomials, we're going to do the same thing that we did earlier, which is we're going to move everything to one side, set it equal to 0, which is called a vanishing polynomial. And then we're going to prove that it's a vanishing polynomial by showing that it evenly divides what we know to be a vanishing polynomial. And it gives a quotient, which is also a polynomial. And we'll move everything over to the side and we'll prove that it equals 0. So it's going to follow the same recipe eventually. So you might not remember, but you do know how, once I write this down, based on everything you've seen in the course up to this far, you should be able to complete this and prove this. But I'll go through how we do it. Okay? And then the first element here, we're going to have to prove that it's 1. Okay? So what we do is we find the first element. So where's the first element going to be in the polynomial? So it's going to be at omega 0, which is 1. So it's going to be here. And then we'll just, how do we prove that it equals 1 at this point? Well, we can just use KZG and open it up at that point.
You know, this has the looks of a deductive proof.
It is. So it's it's a recursive or inductive like kind of proof. Yeah. So this is a recurrence, and then this is the base case kind of thing. So it's exactly that. Yeah. Okay. Questions about this so far?
So you're trying to map everything to a polynomial, like every setup operation.
Yeah, so the recipe is always the same. I start thinking about what a bunch of arrays look like. Then I write down some rules like this times this has to equal this or whatever. If I rotate this over, this times this plus this minus this equals 0 or something like that, yeah? So I start with a bunch of arrays. I write down some rules for how the arrays should behave. That's called a constraint. And then those rules correspond to whatever I'm trying to prove. So I'm trying to prove that this circuit is executed correctly. So I have to write down enough rules to prove that it works correctly, yeah? Then what I do is I turn those constraints I turn the arrays into polynomials, and then I map the rule that I had about the arrays, I map into a rule about polynomials, yeah? Then I commit to the polynomials. I give the verifier just the commitments, not the entire polynomial. So that's what makes the whole thing succinct, right? Then what I need to do is I need to somehow prove that that the constraints are like what's happening in the polynomials. What happens when you have the commitment to the polynomial? If you just have the commitment to the polynomial, you can follow that the rules were applied just by looking at the commitments themselves. Yeah? Okay, yeah. So we're always doing three things. We're thinking about it in terms of arrays, we're thinking about it in terms of polynomials, and then we're thinking about it in terms of commitments to polynomials. And it's kind of like a mirror action. So we do something with the arrays, we have to follow it with the polynomials, and then the verifier has to follow it along with the commitments itself. Yeah. Okay, so these are the two things. So this we know how to do. We just open it, KZG. This we have to prove that this statement holds. Okay, so how am I going to prove that this statement holds? So I'll start with it here. So this is the statement I'm trying to prove. And note that this holds on the domain, meaning this is true for every variable where one of the variables is one of these values. Okay? It's not necessarily true outside of the domain. So the polynomial has a lot of points that aren't on the domain. It's not necessarily going to be true everywhere on the polynomial. Okay? If it was true on everywhere on the polynomial, I could just start opening these up at random values and you could just check that this relationship holds. But unfortunately, it's only true on the domain itself. I don't want to open these values on the domain because then I'm revealing private information, potentially. Okay, so what I'll do is I will just rearrange this equation. So I'll multiply, cross multiply, I'll move this over to the other side. And so now I have it equal to 0. Okay, so what that means is that if you plug in any of the roots of unity into these variables, you should get a 0, okay? Or another way of thinking of it is, if you want to think of all these arrays, I didn't draw it out, it might be a good thing to add, but you could draw out all the arrays and with this relationship, and then what you're going to end up with is an array of all zeros. Okay, so the end product will be 0, 0, 0, 0, 0. Okay, what's the word that we use for a polynomial that's 0 everywhere on the domain? A vanishing polynomial. Okay, so what I want to do is I want to prove that this vanishes. Okay, we've done this before. So before, when we looked at like the add gates, we also had a polynomial that should vanish. So let's see if I can pull out exactly where I read it that way.
Just have to divide it. Once we get the vanishing polynomial by the variable to the power of the minus 1.
Yeah, correct, yeah. So this was the top thing here was the thing that needs to vanish. And so the trick that we use is we divide it by something that we know is a vanishing polynomial, and that should give us a actual polynomial as a result. Okay, I'll show it to you in this case. Okay, so yeah.
When we divide by a variable to the power of k minus 1, are we proving that it's a 0 polynomial that vanishes everywhere, or are we just proving it's vanishing on the domain?
Okay, so what's I'll ask you some questions. What's the numerator here? So the top part.
So it's the
Is it 0 or vanishing?
It's vanishing.
Okay, and what's the denominator?
A 0? No, it's not. Is it a 0?
So think about it. Does anyone know? What is this thing? We've seen it before.
It is all the roots before.
Okay, yeah. So this is a vanishing polynomial. It's one, the thing is the verifier doesn't know whether this vanishes or not. That's what's trying to be proven, right? So I think this is vanishing, but I'm not sure that it's vanishing. This I know for a fact is vanishing. So this polynomial here is, it's basically like this minus omega at 0, this minus omega at 1, or something like that. Let me think. Sorry, no, it's sorry, I don't know. My brain's not working. No, I think that is right. Yeah. And so if you expand it out, we know that this is, I guess let me think. Why is this so hard? Actually, let me just, I can go back and look it up too. Yeah, no, I think it's this. And so if you expand it out, that means it has a root at omega 0, which means that the value at omega 0 is 0. Yeah, so it's this. But anyways, yeah, so if you expand this out, basically all the omegas cancel out, and you get this. You're going to have k of them. That's where the k comes from. So yeah, it will be that minus 1 times that minus 22 times that minus 57, 34 all the way up. Yeah. Okay, so anyways, the point is that this vanishes. The verifier knows it vanishes. The verifier can construct this before the protocol even starts. Okay, and so I'm taking something that's supposed to vanish. I'm dividing it by something that does vanish. Yeah, and if the top thing vanishes, then it's going to have roots. It will have roots at all the same values of omega. Okay, and so they're going to cancel out, and they might have roots elsewhere. So I might be left with something on top, and that's what t is here. So t is the quotient of these two things. Okay. The point is that t is a polynomial, meaning that this evenly divides this. Okay, so when I do all the divisions, I'm not left with anything on the numerator. Okay, I might be left with stuff I'm not left with anything on the denominator. I might be left with stuff on the numerator. Okay, if I'm left with stuff on the top and the bottom, this is not a polynomial anymore. We call it a rational function. And I'm not going to be able to commit to it with KZG and have it like open up correctly and things like that. Okay? So later, the fact that I'm able to open a point on t proves that t is a polynomial. Okay? All right. Then what I'll do is I'll move, again, I'll cross multiply, and then I'll subtract. I'll move this stuff over, change the signs, and I get this whole thing equals 0. Okay, and now finally this is 0 everywhere. Okay, so it's not just 0 on the domain. This is a fact about these two polynomials across all the points on the polynomial, and so that means that when I move everything over, this is 0 everywhere on the polynomial. Okay, all right, so then I can test this now finally. How do I test that this polynomial is the result of this polynomial is 0? Okay, so I pick a random point, and if it's 0 at that random point, overwhelmingly, it's going to be 0 everywhere. Okay, the chances of me picking a random point where it happens to be 0, if it's not a 0 polynomial, is very, very small. And you can compute how small it is, and it's what we call a negligible amount. Okay, all right. Now, the last thing I'm going to do that's going to make the math kind of go crazy and blow up, but it's not that hard, is remember, what's this sigma hat thing? Okay, we have a sigma hat here and we have a sigma hat here. What exactly are they? Well, remember from our diagram way up here, sigma hat is gamma minus the original sigma, the sigma that we have here, plus beta times the c that we have here. Okay, so instead of like producing sigma hat as its own polynomial and committing to it and sending it to the verifier, what I'm going to do is I'm going to replace sigma hat with the original. Okay, then the whole proof for this whole proof, I just have to look at c. I have to look at sigma 1 and sigma 2, and there's not going to be any other. I don't have to look at anything else, any of these intermediate values. Okay, so sigma 1 hat in polynomial form is gamma, which is just a number, a constant, minus the polynomial of the original sigma minus beta times p times the polynomial of c. Okay, and similarly with sigma 2 hat. Okay, so what I'm going to do is I'm going to replace this with this, and I'm going to replace this with this. Okay, and then I'm going to have to multiply the terms out. So it's going to get long. Okay, but anyways, that's how it works. Okay, so if I do it, this is what I end up with. So this is just the straight substitution. I substituted it in, and then if I multiply it out a bit, this is what I end up with. So I have 0 equals the quotient polynomial times the thing I know is vanishing, minus gamma times the accumulator plus sigma 1 times the accumulator plus beta times the circuit trace times the accumulator plus gamma times the accumulator, but here it's omega x, or omega variable, instead of just the variable itself. Okay, so this is the next element. So remember here we had the polynomial at variable, but we also have the polynomial at the next element over, which is omega. So we also have that inside of this. And then anyways, you can go through the last two terms. Okay, so if all of this ends up equaling 0, then I'm happy. Okay, that's actually going to prove that the diagram was wired correctly. Okay, we're going to have to backtrace to see why proving this is 0 proves that the wiring of a circuit is done correctly. We'll do that exercise in a second. But essentially what's going to happen is I'm going to give the verifier commitments to all of these things. Verifier is going to pick a random point, and then I'm going to open all of my commitments at that particular point. or at omega times that point. And then the verifier is going to check for whether at that point it equals 0. And if it does, then it's going to conclude that the whole thing must equal 0. Okay. Questions up to this point? Okay, so I'm going to now just go through the protocol from start to finish, just of the wiring itself. I didn't make a slide or a write-up of the entire Plonk protocol on like one flow, but basically it's going to be this protocol plus the protocol about the add gates plus the protocol of the multiplication gates. Okay, so in order to do this protocol, I'm going to need C, sigma 1, and sigma 2. Okay, so what are those things? So C is my circuit trace. Sigma 1 and sigma 2 is the permutation or the wiring or the copy constraints, however you want to think about it. But it basically tells me that if I have a 5 here, I also have to have a 5 here. And if I have a 42 here, I also have to have a 42 here. And that's based on how this is wired up. Okay, so the wiring here, the fact that gate 1 out is wired to gate 3 in, is captured in sigma 1 and sigma 2. Okay. All right, so I create these 3 as arrays. Then I want to convert them to polynomials. So I'm going to treat each element of the array as an evaluation at the roots of unity here. So I'll say 3 is a point on my polynomial, 22, 5 is a point on my polynomial, 57, 8 is a point on my polynomial. I'll interpolate that and I'll get back the polynomial in coefficient form. I'll do the same thing with sigma 1. So 1, 1, 22, 2, 57, 3, interpolate, gives me a polynomial. I'll do the same thing with sigma 2. So 1, 1, 22, 11, 57, 7, 34, 4. Those are all points. Draw a line through the points. Now I have it in polynomial form. Okay, so I have a polynomial of C, I have a polynomial of sigma 1, I have a polynomial of sigma 2. Now, what I want to do is I want to give this to the verifier, but I can't give them the polynomials. The polynomials could be 10,000 coefficients long. So what I'm going to do is I'm going to commit to them. So I'm going to use KZG, and that's going to give me a single number. So this will be a single number, this will be a single number, this will be a single number, and technically it represents the value of this polynomial at the value tau, which is the secret value that no one knows. Okay, so now I have the commitments to the polynomials, and that's what I send to the verifier. Okay, so the verifier has C commitment to sigma 1 and sigma 2. Now what I'm going to do is I'm going to choose the beta and gamma values. What are those again? So the beta value is the value that squeezes them together, and the gamma value is the value that makes it a root of a polynomial. Okay, so it's in other words, I make a polynomial here, and then a beta is a random evaluation of this polynomial, and then I make a polynomial here, and gamma is a random point or evaluation of this polynomial here. Okay, so either the verifier chooses them if it's an interactive protocol, or if it's a non-interactive protocol, we'll use what we described last time, the Fiat-Schmier heuristic, where we set beta to be a hash of basically all the things that the verifier has seen so far, and we set gamma to be a hash of all the things up to that point that the verifier has seen so far. Okay, then what we're going to do is we're going to build our accumulator polynomial. So we couldn't build this until we knew the division of this, and we didn't know the division of these two elements, these two, until we knew beta and gamma. Okay, so we needed beta and gamma in order to create this number. And then once I had these sigma hats, then I was able to build my accumulator. Okay, so that's why I had to wait until I got beta and gamma. Okay, but it's too late to change anything, so I'm locked in. So my C, my sigma 1 and my sigma 2, I'm completely locked in. Okay, that's why I send it to the verifier first. Then the verifier surprises me with a beta and a gamma. Okay, now I can finish off my side of the things by building the accumulator. Again, I'll interpolate it into a polynomial. I'll commit to that polynomial, send it to the verifier. And then I can also do the step of dividing this vanishing polynomial by this vanishing polynomial and getting the quotient polynomial here. Okay, so I'll compute what that is, and I'll commit to it, and I'll send that to the verifier. So the verifier will have a commitment to these final values. Okay, here I'm building the array first. With this, because it's the result of a polynomial division, I took a polynomial and divided by a polynomial. I don't actually really have it in array form. I already have it in polynomial form, so that's why this step that looks like it should be here is missing. But. Okay, everyone good so far? All right, so now everything is locked in. The verifier has a commitment to every polynomial that will be involved in this proof. What they need to check is two things. They need to check, well, let's go back to the start. They need to check this, and they need to check this. These are the two conditions that they need to check, okay? This first condition turned into this polynomial expression, and this polynomial expression, when we worked it, ended up turning into this polynomial condition, okay? So this polynomial condition is the same as checking that this update rule is being done right, okay? And then the second condition just checks that we started our accumulator at 1, which also proves that it ended at a 1, which proves that the product of everything in this array is a 1. Okay, so how do we do it? So what happens is this is the same as last time. The verifier will choose another point, zeta. And what we'll do is we're going to open all of our commitments at zeta. So I'm going to open z at zeta. I'm going to open sigma 1 at zeta. I'm going to open sigma 2 at zeta. I'm going to open my accumulator at zeta. Skip this for a second. I'm going to open t at zeta. Okay, so I've now opened all the polynomials I committed to, I opened at zeta. Okay, now this recurrence, we also have to look at the next value over. So if we're going to open it at zeta, we also have to look at it at omega times zeta. So I'm going to actually open this polynomial, the accumulator, twice. I'm going to open it once at zeta, and I'm going to open a second time at omega times zeta. Okay. And then the third thing is, for the second constraint, I have to prove the first element is 1. So that I have to prove that the accumulator at omega 0 is 1. And so I'm going to open it a third time at that point. So I'll open this accumulator at omega 0. Okay. So all these polynomials I open once, but the accumulator ended up opening 3 times. Okay. Then what the verifier will do is they'll check. So they now know t of zeta. They can compute zeta to the k minus 1. K is known. They know what gamma is. They were given the opening of the accumulator at zeta. They have the opening of all of these. You can go through. They have it at omega zeta. And so there's no expression here that they don't have, either as an opening, or they just know it because it was, say, a number like gamma beta that they chose themselves. Okay, so they can fill in every term here with actual numbers. Okay, and when they fill it in with actual numbers, they'll check whether this whole relationship equals 0. Okay, and then they'll also check that whatever was opened here is a 1. Okay, and so that proves that the accumulator started at the value 1. Okay, so now I'm satisfied that this recurrence is correct. I'm satisfied that the boundary condition is correct. And so I'm satisfied, actually, of this entire diagram. So what I just got out was a proof that if I start with these 2 values, these 3 values going in, and I follow this whole procedure all the way through this flowchart, that what I get out that they have the same product. I have a proof that that the inputs here are the same product, which in turn proves that the inputs here are set equal, which in turn proves that if you encode these, then you end up with something that's set equal. Okay, so that's the proof itself. Let's just go through the logic of it, and then we can pause for questions. Okay, so what does this actually prove at the end of the day? So it's proving that these two variables have the same product, okay? And it's more like they overwhelmingly have the same product. Technically, there might be some condition where they don't, but because of Schwartz-Zippel lemma, which I'll just say SCL, they have the same product, okay? What does it mean if these things have the same product, okay? Well, what it meant is that if you have a polynomial with roots of sigma tilde, and I have a polynomial where the roots are sigma tilde 2, okay? With overwhelming probability, they're the same polynomial. Okay, again, by overwhelming comes from the Schwartz-Zippel lemma. Okay, if these two polynomials, what are these two polynomials? These two polynomials are what's on the wire here, basically. So these two polynomials here. So what I've proven is I proved that these have the same product here, and then that proves that if I do this roots trick, that all of these are set equal. Okay. Now I want to, basically I'm back tracing all the way back to the start. Okay, so sigma 1 and sigma 2 tilde are set equal. If they're set equal, then when I squeeze together sigma 1 and C, and I squeeze together sigma 2 and C, they're set equal, okay? Because they're producing this, okay? Now it's overwhelmingly because when I squeeze them together, I did this probabilistic trick. So I did a random linear combination. So it's possible that there might be a collision, but there shouldn't be when you make Q big enough. All right. Now, if squeezing these two together is set equal, what that tells me is that wherever a value in C matches sigma 1, the same value in C also matches the value in sigma 2. Okay? So what that means is that C has copies of the same value in the locations that are identified by sigma 1 and sigma 2. So visually, everywhere there's an arrow, okay? If I treat these as locations in C, this tells me the location at 2 and the location at 11 need to have the same value. So the location at 2 is 5, and the location at 11, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 is also a 5, okay? And then you can similarly go through the rest, okay? Okay, and then that tells me, assuming that sigma 1 and sigma 2 are capturing the correct wiring of the circuit, then that implies that the circuit is wired correctly itself. Okay, so I'll pause here, because now we're done with Plonk. Done and final. Okay, so this was the last sort of step. I should have maybe wrapped it up by going back to this list that we had, but I'll just show it here. So in earlier lectures, we proved that public inputs are correct, public output is correct. We proved that all AND gates are correct, all multiplication gates are correct. The last thing we were trying to prove is the wiring was correct, and that's what this does. It proves, all this math proves that the wiring is correct. That's the final conclusion, okay? And so if all of these things are correct, then this circuit is correct. This 32 is the correct output of, 3, 5, 6, 7 being fed through this circuit. It gives you 32 as a result. Okay, any questions about Plonk? Because for the rest of the class, I'm not going to talk about Plonk anymore. Okay, good. Okay, so there's a few kind of random points that I want to talk about, and then I want to use some time also to talk about different use cases of zero knowledge, which is something I intended to sprinkle throughout the course, but I just got busy trying to explain things, and so I saved it all for the end. The first thing is that the Plonk that we saw wasn't zero knowledge. It wasn't a ZK snark, it was just a snark, okay? So how do we make it a ZK snark? What do we have to change about the protocol? And so it turns out it's pretty easy. We have to make 2 changes to the protocol. So the first thing that we need to do is when we commit to things with KZG, we're going to use the Peterson variant. So that's the variant with the extra blinding factor on the end, as opposed to the Feldman variant, which doesn't have the extra thing, okay? So that's almost done. It's almost like if you just switch the polynomial commitment so it's perfectly hiding, then, or it's at least hiding, whether it's perfect or not, then you're done, more or less, okay? But there is one sort of corner case. It happens to do with the fact that we're opening, in the protocol, we open polynomials. So like, I'll take this as an example. I open this polynomial C at the value zeta, and I show that. So the verifier knows what this polynomial is evaluated at zeta, right? Okay. Now imagine a world where C is supposed to be secret. So no one's, the verifier is not supposed to know what the value C's, any of the values in C are. Okay, or at least the ones that aren't opened up to them. Okay. Does opening a polynomial constructed from C at some random value zeta, does that give any information about what's in C? Does it leak any information about what's in C? Okay, so I see shaking of heads more than nodding of heads. So first off, notice when I choose zeta, I didn't write it as an explicit condition because it's usually going to be true probabilistically. But when I ask for an opening at a random value, I'm not allowed to choose like 34 or 47 or one of these values. Okay. If I choose a domain value, then I will learn. I could learn that like there's a 42 here. It won't tell me the whole thing. But zero knowledge is very strict. The word zero in zero knowledge means you leak 0. Okay. So we want to leak 0 about the contents of this. So when I choose zeta, I'm not allowed as a verifier to choose a zeta value that's part of the domain. Okay, otherwise I'll learn something about what's there. Yeah.
Well, if you were to choose the point like completely randomly,
Yeah.
is it possible that you just happen to?
Yeah, so we're going to consider that it goes in that like overwhelmingly not possible type of thing. Okay, so now I'm choosing zeta, and it's not going to be in the domain probably. It's going to be some random point somewhere else on the polynomial. Does that tell me anything about the values that are in the domain? So first off, it doesn't directly tell me anything. We can all agree, right? It's just a random point in somewhere else. It's not going to directly tell me what any of these values are. Okay? But indirectly, could I infer something about it? Okay? So here's a thought experiment. Let's say I have a guess at what this is. Okay? So I have a guess. I think these are all the values, but I'm not exactly sure. Okay? Then I do Plonk, and I get a proof, and it has a bunch of openings and things like that. Should I be able to tell at the end of Plonk whether my guess was right or wrong, if the protocol is going to be zero knowledge? I shouldn't be able to tell, right? If at the end of the protocol I can confirm whether my guess was correct or not, that leaked a bit of information, like literally 1 bit, which is either this is right or wrong. That was leaked as a result of it, okay? So what would happen is I would guess at what C is. I would interpolate C. I would get some polynomial, right? Then I would go say, open it up at zeta. I would choose a random zeta, so it has nothing to do with the domain, okay? The prover will tell me what the opening of their C is at zeta. Then I'll go back to my polynomial. I'll open it at zeta too. And what if those 2 values match? Then I know for sure my guess was correct. Overwhelming by Schwartz-Zippel lemma, okay? So I know that my guessed polynomial and the prover's actual polynomial were the same, because there's no way that happens just by coincidence, okay? All right, so I actually have a problem. If I open C up at some random point, I could leak whether a guessed polynomial is correct or not. Okay? So the second thing I want to do is I want to fix that. It shouldn't be possible to confirm whether your guess is correct or not. Okay? So the trick is pretty easy. The reason the trick works is because when the prover interpolates C, and when I interpolate C, we get the same answer. Okay? All right. Now, is there only one polynomial that would run through all of these points? No, there's like an infinite number of polynomials, right? So what I got to do is I got to interpolate and get my polynomial, okay? Then instead of using the output of interpolation, I have to pick another polynomial that is the same. It runs through all of these points, but it's a different polynomial somehow. Okay, and I'll just choose it randomly. Okay? Then if I do it with my guess, I get stuck at that point because I can't guess what the polynomial is that they turned it into. What's the random polynomial? Okay? And there's too many guesses, I can't try them all. All right? So how do we do that, like sort of mechanically? What we do is when I interpolate, I use these as a set of points, and then at the end I just make up a couple extra points. Okay, so I choose at random some x and some y, some other x and some other y, and I can do a couple of these points. And then now I'm going to interpolate the polynomial through all of these points and also through these sort of extra points. Okay? So I'll have some extra points, I'll run the polynomial through them. And unless if the guy who's trying to, or woman, like the person, the verifier, the malicious verifier is trying to, if they're trying to guess what my polynomial is, unless if they choose the exact same x and y, they're going to get a different answer. Okay, so they'll always have a different polynomial, even if their guess is correct. Okay, so if they guess wrong, the polynomials will be different. If they guess correct, in terms of having all of these values be correct, because of these extra random values, the guess is going to come back wrong anyways. Okay?
Are they just random, or do they also follow the roots of unity?
So they cannot follow the roots of unity because we've used all of the roots of unity. So here we have 15 of them. Yeah, and so and that's why it wraps back. So these are going to be off domain points. Yeah, and then we're gonna choose them. Okay. All right. I'm just going to not keep this here because it's going to be confusing when you download the notes. But I wrote it out. Oops. Okay, so every time you open a polynomial, like say at zeta, but especially when you open a polynomial more than once, right? So like here, I was opening the accumulator at zeta, and I was opening at omega zeta, and I was opening at omega 0. Okay, so I had 3 openings. Then what I need to do is I need to add at least 3 random points to my polynomial before I interpolate. And the best advice is to add 1 extra, so add 4. If you open a polynomial 3 times, add 4 points. Okay, so I add random points off domain to what is interpolated or before interpolating it. You can also interpolate first and then kind of add it as a random polynomial, which ends up being a better way of doing it because of this kind of messes up your ability to use fast Fourier transform. It's just technical detail that don't worry about. But so what I'm going to do is I'll add, if I open a polynomial, I'll go through my protocol, I'll see how many times do I open that polynomial. So I saw I opened accumulator 3 times, okay? When I look at my add constraints, right? This polynomial C, I'm opening at lambda and at a lambda omega and a lambda omega squared. So I'm opening that one 3 times too, right? So these are all the polynomials that when I interpolate them, I have to add like 4 extra points. Okay, so if I see that it's opening at m points, I'm going to add m plus 1 extra points to the polynomial. It kind of blinds the polynomial or randomizes the polynomial, and then it stops this attack. Okay, so Plonk, if you consider it a snark, not a ZK snark, it out of the box as a snark, it all molds is 0 knowledge. okay? It's very, very close to being zero knowledge. The only thing you have to do is you have to swap out the commitment scheme to make sure it's hiding. Yeah? And then this extra trick. Now, if you miss this trick, right, it might not matter. I mean, like a lot of circuits, you're talking about 100,000 gates or something like that. Like people probably aren't going to have an exact guess. It actually doesn't matter how many the gates are. It's more about the inputs. But people may not have an exact guess anyways. And so it's not like it leaks everything about the circuit, right? It only leaks like whether an exact guess is correct or not. So whether that is a problem or not for your ZK snark, you can think about. But in crypto, we always do the best thing, right? We always make sure that it's secure in all settings, okay? So what you need to do is you need to also randomize the polynomial too. Okay, so now we have a ZK version of Plonk, and we all along we had like just a normal snark version of it. Okay, one other tidbit I'll talk about quickly. Yeah.
Can you say more about add n plus 1 for polynomial is open at n points, the last thing there. Add n plus 1 what? Points?
Oh yeah, sorry, add m plus 1 points. Thank you.
So we're basically doubling the size.
Not doubling, we're adding 1. Well, if m is 1, we're doubling, but think of m as 5, we're making it 6.
Okay, so we're adding 1.
Yeah, so we're just adding 1. So if we open it m times,
Because we're going to bring in basically, in total you get 2 m plus 1 points. But you want just m plus 1 total points? Or
okay, let me make the grammatical correction and then I'll answer. Okay, so add n plus 1 points. The problem is I also have points here twice. Let me just fix the English and then I'll answer your question. All right, so we're going to add n plus 1 random points to a polynomial.
Open m times.
Yeah, thank you. That is opened m times in Plonk. Yeah, so like the accumulator I opened it 3 times. So before I turn my accumulator into a polynomial, I would add 4 random points to it. And then I would interpolate just through the domain plus through those 4 random points. And then that's the polynomial I'm going to use. It's a polynomial I'll commit to and I'll give to the verifier.
so the more you open it, then the more points you have.
Exactly, yeah. So in like if this was all there was to Plonk, I would only add 2 points to this to sigma 1 because I'm only opening it once, but I'm adding 4 points to the accumulator because I'm opening it 3 times. Yeah.
But on this ruins and properties we saw before the midterm when we talked about transformation matrix.
Yeah, so the only thing it ruins is exactly that, is the FFT. So normally what you'll do is you'll first interpolate the polynomial using FFT without adding the random points. Then once you're holding that polynomial in your hand, you'll add the random points in a way that it doesn't mess up the domain values. It only messes it up outside of the domain. And that's cheaper than like using Lagrange or some other interpolation from the start kind of thing. Yeah. The other trick you can do is you can have sort of 2 roots of unity. You can have like a sort of inner root of unity that you're using for Plonk, and then an outer one that you're using for FFT. So it gets complicated. You can dig down on like how you do that, but that is the exact property it messes up. Yeah. Okay, the last thing I'll talk about before the break is this a quantum safe protocol? So we all hear about quantum computers coming. And so the answer is no. It's based on the discrete logarithm problem, and the discrete logarithm problem can be solved by a big enough quantum computer. Okay? So let's say we wanted to make this quantum safe. How much of the protocol do we have to change? Do we have to change the whole thing, or can we just change pieces of it? So it turns out, this is why I like this protocol as well, is the only time we use the discrete logarithm is when we commit to polynomials. Okay? All the extra stuff, like all of this stuff, like opening polynomials and checking these equations and things like that, it has nothing to do with the discrete log problem at all. It has nothing to do with cryptography even. Okay, so if we want to make this post-quantum, we just have to swap out KZG with a polynomial commitment scheme that's post-quantum if such a thing exists. And then we can do Plonk exactly the same. Okay, the rest of the protocol is identical to it. Okay, and so it turns out that there are post-quantum polynomial commitments. The other thing we can ask ourselves is, what do we need from the polynomial commitment? And so for Plonk, all we need to do is we need to open at a random point, or at a point in general, an arbitrary point. Okay, so that's what we need from the polynomial commitment scheme. KZG had some extra features. For example, if you had commitments to polynomial A and commitment to polynomial B, you could create a commitment to A plus B without knowing A or B. So it had this like homomorphic property. We actually never used that in Plonk. We only used it to open, KZG's own opening proof uses that property, but in Plonk we never used it, okay? Or the multiplicative homomorphic property, or the bilinear pairing. Like we never used any of that stuff, except for when KZG used it itself for its own opening proof, okay? But on the Plonk side, all we did is commit to polynomials and open them. Commit and open, okay? So there's at least two post-quantum polynomial commitment schemes. One that's like very well known and old, like fairly old, like I don't know, maybe 10 years now, is called Fry, and there's a variant called Deep, which just takes care of some security stuff, kind of like this, some red tape around it. It's based only on hash functions, so that's it. So there's no crypto anywhere, there's no discrete log or anything like that. And hashes are conjectured to be quantum safe, and the way that they're used in this protocol is conjectured, and so it is believed. It's always just a belief, but it's believed. It's a very strong case that it's post-quantum. Now you might say, well, why didn't I teach you it with Deep Fry? Why did I teach it to you with KZG? And so there's two answers. The first answer is that Fry, even though it looks simple because it's just based on hashes, it's actually very complicated. So the way you use the hash functions it's a lot more complicated than KZG, in my opinion. KZG is nice because you just have some exponents that add and multiply and things like that. Fry is like very complicated. You have this whole hash tree, and you have to prove, like, you have to do this folding mechanism and things like that. It's a complicated protocol. So I taught you KZG because it's easier. Okay. The second is from a performance perspective. Deep Fry is way worse than KZG. Okay. So it's not constant time. It's constant size. Sorry, it is constant size, but when you open, the opening proof is not constant in the degree of the polynomial, and the amount of time the verifier has to take is also not constant. It is logarithmic. Logarithmic is super close to being constant, but it's not quite constant. And then if you don't care about what we call asymptotic behavior, if you care about like wall clock time and like size in memory, these things are like hundreds or thousands, like hundreds of megabytes, maybe megabyte kind of thing. I forget the exact ranges. Whereas like Plonk is like very, very short. It's like, I forget the exact size, but it's like in bytes, like it's quite small. Like concretely, if you're passing a lot of proofs around, you are passing around kilobytes of data now instead of like a very small thing. And you're spending a bit of time verifying it as well, okay? There's one's based on hashes, and generally, this is generally true of all post-quantum stuff, whether it's signatures or other things. There's kind of like two families. There's the hash one, which are really expensive, and then there's a set of problems that are kind of like the discrete log problem. It's a hard, intractable problem, but they're based on these things called lattices. And so one of the most popular, efficient ones is called modulo short integer solution. It's just, think of it as like the discrete logarithm problem. It's some lattice-based problem where it's hard to find values that satisfy a certain equation and are short in this case. Okay, so there's some hard problem. And this is thought to be hard not just for a classical computer to solve, but also a quantum computer to solve. So it's a hard problem for both settings. Okay, And so there's a lot of signatures and other things that are based on this assumption. And now people have been trying for the last, or they've succeeded on making polynomial commitments that are based on this assumption. And every year there's a new one. So today, 2026, Greyhound is kind of the state of the art. But last year, if I was teaching this course last year, I would have said, the name escapes my brain. But anyways, there was a predecessor to it, and then the year before there was something else. And so they're still like kind of getting faster and faster. Whereas Fry has been kind of the state of the art in Hashbase. There's some little variants on how to make it efficiently, but it's more or less still Fry today. That's the same. It's the same algorithm itself. So by next year, this might change. There might be a new, better candidate. Okay. These are much more efficient and faster than Fry, but they're not nearly as efficient as KZG. So if you want to think about it, like KZG's the best, and then like Greyhound, those types of things are kind of in the middle, and then Fry is, I'll just write Fry. Fry is kind of like the slowest in terms of performance. And performance corresponds to prover time, verifier time, and proof size. Those are the sort of three things that we look at. So should Greyhound just completely replace deep Fry? So this module, SIS, isn't as well studied as hash functions. And so people they're not sure that it's exactly correct, or there's still, people worry about whether this is actually post-quantum. And there have been some other like lattice-based like hard problems that were supposedly hard that ended up not being hard. People found quantum algorithms for it. So that's the main reason I think that people might still continue to use Fry instead of using Greyhound. This also has only been around a year, and so even if this assumption is correct, maybe there's a problem in the protocol itself or the scheme itself that people haven't identified yet. So, it's not like everyone's switching immediately to these other ones. Okay. So Plonk with Fry is like a very common configuration. So there's a library called Plonky2. And it's basically Plonk plus Fry. And then the Plonk here has some extra gates. So we talked about just addition and multiplication. They also introduced what are called custom gates. So sometimes we call that turbo Plonk or hyper Plonk, I forget which is which. Turbo Plonk, I think. And there's these like lookup gates, and there's a few extra things that you can do. So it's kind of a fancier version of Plonk, plus you switch it for Fry. So that's Plonky2. There's a Plonky3, but Plonky3 lets you choose. So it just says choose your own thing here. We're going to use like the Plonk style arithmetic, as it's called, arithmetization. But you can choose your own polynomial commitment scheme. So if you want to use Greyhound, if you want to use KZG, it's up to you. The other advantage of these two things is, remember KZG had that trusted setup. These two do not have a trusted setup. Okay, so that's another big advantage of them. And so sometimes we call them STARKs instead of SNARKs, where the T stands for transparent. And that's just a hat tip to the idea that there's no trusted setup. So if you see STARKs as a term, usually it strictly means there's no trusted setup, but normally it means there's no trusted setup and it's post-quantum as well. But there are STARKs, like bulletproofs or something like that, that are not quantum safe, but are transparent. So anyways, but yeah, so there's a company called Starkware. They make STARKs based on Fry. And so that's like one popular branch of the ZK world. Plonk with KZG is sort of another popular branch. And then there's other branches that are popular. So Plonk is actually only one protocol out of like a pretty big space of protocols. But it's a pretty significant one. It was also the one I felt was easiest to teach end to end.
So the start is succinct.
Transparent. Yeah, and then the T replaces the end, but they're still non-interactive. They can still be made non-interactive in the same way. So It should technically be a SNARK or something like that, SNARK, but anyways. Okay, questions about this quantum safe stuff? Okay, so let's take a 10-minute break, and then when we come back, I'm just going to talk about use cases of SNARKs for the rest of the class. All right, we'll wrap this up. Okay, yeah.
What you explained is part of the project, right? I mean, one of the items was to go with the concepts.
So you mean the post-quantum stuff or the use case stuff?
The different branches of extensions.
Yeah, exactly, yeah. I can't, it's so long since I wrote the project, I forgot that I had did that, but yes, yeah. It's quite possibly true. Okay, oh yeah, there's one other thing I was going to show you. So there's a lot of tooling around zero knowledge stuff, including, so you maybe have encountered this in your project or not. So one that does Plonk kind of under the hood is called Noir. So it's from Aztec, I believe, which was affiliated with some of the people who made Plonk. So like, for example, this is just, I'm not going to go through this in any detail, but just to sort of give you an impression of what you can do. So they have like this, instead of defining a circuit, you can just write out code. So this language here is constrained. It's not like a general programming language. But if you learn the constraints of the language, this is a very simple SNARK that just proves, almost like we were doing it, proves that two values, I forget exactly what it is, like some value times two, an addition and a product. I can't really understand what it is, but anyways. So you have two inputs, X and Y. You can specify which ones are public, which ones aren't, and then you can encode up your logic, and then a tool like this will spit out. So this is actually what the proof, for example, looks like as a value. Kind of a long value, but that's the actual proof itself as a blob and things like that. So anyway, this is called Noir. There's a lot of other ones. So depending on where you want to program, you can essentially choose between three sort of locations. You can program at the circuit level. So if you know exactly what the circuit is, you can go to Circom's probably the best and program it as a circuit. You can program it in a scripting language like this, and it will compile down to you. And then if you don't want to learn a whole new scripting language, you can also code in any language of your choice, C, Rust, Java, whatever. And there's something called the ZKVM, which will, it has basically circuits for every single opcode operation in a standard VM. So like RISC architecture or something like that. And then it will convert your C code into opcodes, and then it will turn your opcodes into circuits, and then it will turn your circuit into a proof, whether it's based on Plonk or whether they tend to be based on a different kind of branch in the zero knowledge tree. Why would you choose one or another? Mainly performance. So if you program the circuit by hand, it will probably be a pretty fast circuit. If you use a scripting language, it might be a little bit faster than if you use a general purpose language and a general purpose compiler. But a general purpose compiler also, you don't have to worry about any of the details as well. So there's sort of a trade-off between performance and how friendly it is towards developers. Another thing you can do, actually what I do in my research, is we don't even think about circuits. What we do is we just program polynomials like this that are supposed to do certain things. So we figure out what we want to prove, and then we write it out as like a set of maybe 20 polynomials like this that should vanish, and then that's the proof itself, and then we prove that they vanish. So that's like an even like deeper level where you can program at it, but it's not that flexible because you can't always capture like very complicated things in these polynomials directly. Okay, so use cases, I'll just go through some of them. Hopefully during the assignment you at least saw the titles of different things, and so you got a sense that it's a pretty big field. And this is also the reason why I like this course, or I wanted to teach a course on it, is because it is broadly applicable. It's not just like a security thing necessarily. You could do it in all sorts of different scenarios. So the first is like verifiable computing. So let's say you have a constrained device. It just can't execute an algorithm, or maybe it's like a really complicated thing that you want to execute. You can outsource it to someone more powerful, and you don't have to trust them. Now, trust here, I mean for integrity. So you're going to tell them what you want them to do. They're going to give you an answer back. And if they give you a proof, then you know that the answer is correct. This sounds like a scenario where ZK would help, the zero knowledge property. It actually doesn't help exactly in this scenario, because if the cloud is doing the computation, in order to generate the proof, they need to see all the inputs and all the intermediate values and everything like that. Okay, so just like here, like the prover has to know all of this stuff in order to do the proof, right? And so it's the same thing here. There is a related technology called fully homomorphic encryption. We briefly talked about it. That would also work for privacy as well. So there you would encrypt your program, you would give it to the cloud, it would execute it under encryption, and it would give you back the answer still encrypted, and then you would decrypt it itself. But fully homomorphic encryption is like very not efficient for anything that's like moderately complicated. Okay, so this is a general use case. So it's a use case of SNARKs as opposed to ZK SNARKs.
So what do you mean by the comment here, fully homomorphic encryption?
Just fully homomorphic would work if you wanted to have like sort of a ZK style. If you wanted the cloud to compute something without learning what it's computing, then you could use fully homomorphic encryption. If you're happy letting the cloud learn what it's computing, but you still want a proof that it did it correctly, then you would use a SNARK. And if you fully trust the cloud, you don't care about privacy or integrity, then you would it would compute the answer and give you the answer, and then you'd say that's fine, which is what we do mostly, right? Okay, so for the project, when I described the project, I kind of went through ZK TLS, ZK email, ZK PDF. I think I had it in a lecture somewhere else, so I won't go over that again. But roughly speaking, anything that you can fetch on the web, anything that comes to you in an email, anything that's in a PDF, you could prove things about it using ZK SNARKs. So you wouldn't show the entire thing, you would just show like exactly what you want to prove, and that's it. There's a lot of work on this idea of maybe we have digital identities, so like I think of it as a digital driver's license or something like that. Also just records in general, like say you have medical records and things like that. What you could do is you could have it in a format where it's signed by whoever issued it to you, so your ID is signed by the government, your medical records are signed by a doctor or hospital or...
Sorry, when
Yep.
you have the verifiable computing for the cloud computing,
Yeah.
what if you have a protocol where the cloud computing kind of has some checkpoints where so it can produce a trace that can then be verified?
Yeah, so you can checkpoint and you can, so I guess there's two things. So one thing is there's like a random audit style thing where you can say, okay, compute the whole thing. I'm going to just check it at 10 locations randomly. And if, yeah, so that's another type of approach. It gives you properties similar to zero knowledge. The term we use in crypto for that is a cut and choose protocol. Cut and choose, yeah. And so you basically, you sort of open it up at certain points. And if what you're looking for holds at those points, you conclude it holds at the whole thing. The general trade-off with that is the soundness at the end, you're not very, very confident. So you might be like 75% sure, or 90% sure. Whereas here you're 99.999999999, like 29% sure. And so the confidence of a zero knowledge proof or the soundness, integrity is exponentially high. Whereas in those cut and choose ones, you can get like reasonable confidence, but not like near certainty kind of thing.
So the decrease in confidence in that mechanism is because of the cut and choose. But what if you verify every single thing and you don't do random?
Yeah, so you can always rerun the computation yourself. So checking everything. So another thing that your thing reminded me of is you can also kind of chop a snark up. So let's say that you want to give a snark for a big long computation. What you can do is you can verify it for the first chunk, and then have another snark for the second chunk, and another one for the third chunk, and then you can kind of merge those snarks together. So there's a line of work that includes things like recursive snarks, something called incrementally verifiable computing. There's a technique called folding, where you sort of fold two proofs to produce a new proof that's related. It's not exactly the same, but it's sort of related to that. And so that whole branch looks at how you can sort of chop things up so that it makes it more efficient for the prover, usually is the concern there.
But if we stay within the realm of the traces I was mentioning about, which is not exactly SNARK kind of, you said, was the weakness of it because you were only doing a random audit? If you do a 100% audit, does that increase the confidence?
Yeah, then you're 100% sure.
Yeah, just
Yes.
as if we hadn't done a SNARK.
Yeah, but you spent checking, like say that it's 1,000 steps long, you spent time 1,000 checking all 1,000 steps. So you're 100% with 1,000 spent. Yeah. What a SNARK gives you is 99.9999% with like one check, essentially. Yeah.
Okay.
So that's the trade-off.
And the reason why you would do the random audit is a matter of saving some computation time.
Yeah, exactly. Yeah,
So,
that's it. Yeah.
What is there a typical proportion between a random audit and a full audit? Is there like a 10 time go up or a 100 time go up? Is it quantifiable?
So it depends on how you randomize the audit itself. So there's clever tricks that you can play. So technically a cut and choose is a little beyond just a random audit. It's structured in such a way that if the person's tricking you, they're going to get caught. You want it to be like there's it's maybe easiest to say mathematically. So let's say you're going to check 20 things, right? You can have the probability of getting caught be like 1/20, which is kind of okay. Or you could have it be 1/2 to the 20. If you can get it 1/2 to the 20, then that's actually a pretty good audit. So that's what cut and choose does, is it kind of structures things so that when you open things up and looking at it, the things that you're looking at kind of touch everything else. So that by looking at this one thing, you're not actually just looking at one thing in isolation. You're looking at something that was combined from everything else. And so it's telling you something about the whole thing, even though you're only looking at one piece of it. But yeah, that's sort of at a rough level.
Yeah. Because for an expensive computation, a full replay for SNARK purposes is very expensive.
For the prover or the verifier? For the prover, it's much more expensive than running it. Like quadratic, think of it, like sort of, or n log n, yeah. Yeah. Okay, and so actually to pick up on that point, another place that it makes a lot of sense is if there's multiple people that want the same proof. So then one person does it, they run the proof, and then they give the proof to everyone else. So if everybody's kind of looking at the same thing and they want to do the same computation, then it's sometimes cheaper for just one person to do it with a SNARK, and then it saves computation of everybody else from having to redo it. So I have an example coming up of that type of dynamic. Yeah, that's the example, yeah. So if you think of a blockchain, I'll get there, but yeah, that's exactly the right example, yeah. Okay, credentials, records, so it could be your medical record, it could be a credential, it's usually signed. And then instead of turning over the entire document, you could prove things about it.
Isn't that just ZKPDF?
So it's ZK PDF if these are in PDF form, yeah. And if they're not in PDF form, usually they're in, because you can control the form that they're in, you can put them in a friendlier format where it's actually like structured data. Like think of a JSON file or something like that, like where it's, or XML or something, yeah. Another thing that I worked on is proofs of solvency. So this is like, say you have a bank or a crypto exchange, and a bunch of people have money sitting on the exchange, and the exchange controls some amount of Bitcoin, say. That's on a blockchain and it's all digitally signed. So in theory, they could prove that they could prove what Bitcoin they own and how much they own without revealing it. Okay, so they could say, I know the secret private keys that have signing authority over $1 million worth of Bitcoin. I'm not going to tell you which addresses belong to me, but I can wrap that all up into a SNARK. And then on the liability side, they can also do some stuff as well. So this works because it works well with crypto because, again, the common theme between these three things is everything traces back to something that was signed. Right, so this is a signed PDF, this is a signed email, this is a signed digital identity, it's a signed record. Money isn't really signed. You could use zk-TLS to prove stuff about your bank account, because then it's going to turn it into something that's signed. But in Bitcoin, like everything is signed as well, and so you can prove things about Bitcoin directly because it's signed. Another thing is voting, elections, something else I work on. So normally we have a secret ballot. So what that means is nobody should know how you voted. Usually that includes the government themselves or whoever's counting the votes. In that case, ZK doesn't really help you because there's no prover. The prover has to know everything. But if you relax the condition and say, well, I'm okay with the government seeing all the votes, maybe they're not attributable to me, so they're anonymous, we're not sure who they belong to. But if the government can see all of them, they could prove that the tally is correct without showing everybody all the votes. They could just say, I know a set of ballots, I've seen them, and if you add them all up, this is the winner of the election. So you can use zero knowledge in that case. We mentioned this before, but like higher end cameras will take a picture and sign it, again, going back to signatures. And so when you post a picture on the web, you can prove that it was signed by this camera, or maybe it went through some transformations, like it was cropped and the color was corrected and things like that, but nothing else was done to the picture. It wasn't AI generated, it wasn't like photoshopped, it just traces back to the camera itself. Yeah.
When I was reading about this, I saw there were two different types of keys. There was a public camera key and a private camera key.
Yeah.
What is the difference between?
So in signatures, so this is a signature question, not specific to photography, but the way digital signatures work is you sign something, you use your private key,
Yes.
so I get it from you. I want to know whether that signature is correct or not. I don't know your private key, so I can't reproduce it. So I need to know something about your private key in order for me to check whether it was you that signed it as opposed to someone else. That's your public key itself, yeah. So your public key is kind of like your identifier, and then your signature is the private key.
Yes.
Yeah. And if you take 6110, you'll learn about all of that eventually. Another thing would be sort of on the cash side or digital, like if we think about cryptocurrencies. A lot of cryptocurrencies like Bitcoin, every transaction is written in a blockchain. So you don't necessarily know who the person is that holds it, but you see like this address moved it to this address, and then this address moved it to this address. So you can trace it all the way through. So some people have built more private versions of Bitcoin or other kind of cryptocurrencies. Zcash is a good example. And a lot of work on SNARKs actually came from the Zcash. They were one of the first projects to use zero knowledge, like the newest SNARK. They're probably the first ones to use SNARK in a major project. And they invented a lot of the technology that we have for that project. Here what you'll do is you'll put your money in a big pool that has a bunch of people's money in it. And then later, if I put $10 into the pool, I'm allowed to take $10 out of the pool. But I have to prove before I take $10 out that I put $10 in. Okay? In order to prove it, I could point out the transaction where I put the $10 in, but now I don't have any anonymity. So what I'll do is I'll use a zero knowledge proof instead. I'll say, I know of a transaction where I put $10 into this pool, so I'm entitled to remove $10, and I haven't removed it yet. That's the other harder, little trickier bit, is I haven't removed it yet from the pool. I'll publish that as a proof, and then the protocol will say, okay, you can have $10 because you've proven that you put it in. But nobody knows which, you're taking $10 out, but no one knows which $10 you put in previously. Question? Sorry, what? Yep. So Zcash, so Tornado Cash is another example of this exact protocol. So the way it worked is you had Bitcoin first. Bitcoin didn't have this like level of privacy. Then you had Zcash, and Zcash is its own blockchain. So it's an alternative to Bitcoin. Then maybe Ethereum came out first or Zcash, I forget which, around the same time. Ethereum came out and lets you do smart contracts. And then someone said, well, what if we take Zcash, instead of having it as its own separate cryptocurrency, what if we take what it's doing and put it in a smart contract that runs on Ethereum, then people could mix their Ether using the same technique. And so that's what Tornado Cash is, effectively. It's just Zcash running in a smart contract on Ethereum for Ether. Web traffic. So a lot of organizations want to inspect your web traffic to make sure you're not going to websites you're not supposed to, or there could be any sort of content rules. So instead of having them inspect, if they inspect it, they have to break the encryption. So normally I have end-to-end encryption from my computer all the way to whatever website I'm on. I have that because of this TLS, right? So the TLS here is what gives me that end-to-end encryption. So traffic inspection, say Concordia was inspecting traffic. First off, they can see all the domains that you're visiting because TLS doesn't hide that because the packet has to find its way to the right server anyway, so you can't possibly hide that information. But the actual content of it, they couldn't inspect because of TLS unless that they broke TLS in the middle. And there's different ways of doing it. Usually they can't do it without you knowing about it, so they would have to modify your computer or something to do it. But anyways, instead of that whole model, we could just have a model where your browser is proving to Concordia what its web traffic is. So Concordia sees an encrypted packet go out, and then there's a little proof in plain text that says, by the way, this packet complies with all your rules. It's not going to one of these websites, it's not this kind of content or whatever the case is. Okay? Then no one has to inspect anything, Concordia is happy. So those, sometimes we call them ZK middle boxes. Middle boxes, because it's like the inspector that sits in the middle is considered a middle box because it's in the middle of your connection. Yeah. Blockchains is another example. So there's two. Yeah.
Middle box. So they can see the request before the TLS?
No, so what happens is the standard configuration is before you have TLS, you have to tell the website that you want TLS. So the very first step is I go to Google and say I want to speak TLS. Google will send back a certificate, and then I'll end up speaking TLS with Google, because I use their certificate. What will happen is the middle box will drop in its own certificate. It'll say I'm Google, but it has a certificate for itself. And my computer, because Concordia gave it to me, will be configured to always accept any certificate from the middle box, even though they're not right. Yeah. So then I end up with just an encrypted channel to the middle box. Then the middle box can decrypt and re-encrypt and have an encrypted channel to Google. I don't know, but I can't see that from my computer. But that's normally what it would do. Yeah. But the point is, it can decrypt everything in the middle.
Yeah, but it's not really the best solution, right?
Yeah, so it's a privacy, like, very bad solution from a privacy perspective. Yeah, so this is why the middle box is much better, because you can directly prove it yourself. Yeah, so no one has to break your TLS connection, and they don't see anything beyond that, the fact that you're complying with the policy.
So the proof is being done by the user.
Yeah. So your browser will do the proof, because the browser sees, sorry, so that was maybe the part that wasn't clear. Your browser sees everything before HTTPS, because it's the one that's encrypting it. So it will look at what it's doing, it will issue the proof, and then the proof will travel along with the packets. So, yeah. Okay, two more. So a blockchain is correct. So there's two ways that zero knowledge shows up in a blockchain. One of them is a blockchain is really long. Like Bitcoin's blockchain has been running for over 10 years. And if you want to verify it, you have to start at the beginning and go all the way to the end. So what I could do is just give you the latest block and a proof that everything before it is correct. Okay, so you always just have like a constant size proof. So there's some blockchains that do that, like Mina is an example where you only have to get the latest block, and you don't even have to download the whole block, you just need a hash of the block, which is called the block header, and then you get a proof that it's correct, and then you don't have to check anything. And then the other thing you can do is you can, let's say you take a bunch of transactions offline and you execute them because it's faster, then what you can do is you can prove back to the blockchain that you executed those correctly. So you roll up a bunch of transactions and then you occasionally prove back to the blockchain that you executed them correctly. Then not everyone on the blockchain has to check every transaction. So these are called ZK rollups, and that's another, so these are the two main applications of zero knowledge, plus the Tornado Cache here. And then a final example, I wanted to put machine learning in somewhere. So there's a lot of people interested in machine learning plus crypto, machine learning plus blockchain, machine learning plus zero knowledge, because they're all kind of like buzz terms. There's not a lot of like great overlaps between blockchain and AI that I can see. But between ZK and machine learning, there are actually a lot of sensible ones. So anything that you're doing with machine learning, if you want to prove that it was done correctly without revealing everything, then that's an application of ZK. So if I train a model and I can prove to you the way I trained it without telling you, like without giving you the training or necessarily the model itself. So these are some examples that people are interested in.
But inference would be much lighter to prove than training, right?
Sorry, yeah, I actually know zero about machine learning, so I don't even know what inference means.
Okay.
But it sounds correct. Okay, anyway, these are all the use cases. Any questions about them? Okay, two logistical points. So first off, course evaluations, please fill them out. They're useful to me. This course in particular, I'm not sort of on the fence about whether it was a good experience or not.
It was a great essential.
Okay, but this is a biased group as well, because you're the ones that come to class. The people listening online might have a different opinion about it, but I'm honestly on the fence of whether I should continue teaching this, try and turn it into a permanent course, or if I should just decide it was too technical and too hard. So anyways, your feedback, you don't have to tell me now, you can tell me through the course evaluation itself. And the other thing was your project is due today, right? Is everyone happy with that? Does anyone want more time?
2 more weeks?
I can give you 1 more week, I'd say. If you want, so 2 weeks is when the exam is?
Yeah.
Okay. Yeah, I can make it, I don't want to make it do the same day as the exam because then you'll be balancing both, but how about like a day before the exam?
Yeah, sure.
2 weeks minus a day?
Yeah.
Yeah? Okay, all right.
That's great.
All right. Also, the other thing is, usually, sometimes I do it after the exam, but I have 3 courses and everything's piled up that week. So now all my projects and all my courses and all my exams are in the exact same week, and it's going to be a nightmare to mark everything. So a day before the exam is actually, I'll make it do the same day as the exam, and then you're adults, you can figure out how you want to balance that. That's it.
And you will be grading the projects, not your TA?
Yeah, so the TA does the project and that's it. Sorry, does the assignment and that's it. I do the exam, the 100% of the exam. Well, a machine will mark part of it. Me or a machine will mark it, and but I'll feed into the machine what the right answers are. And the projects I mark myself as well. The exam, by the way, is now posted on Moodle. So it's the wrong. So April 23rd. It starts at 9 a.m. So keep that in mind. So it's a little early than class, and the project I'll change right now
We have
before I forget. Sorry, say it again.
the whole table.
The whole table?
No syllabus. Is it the whole syllabus? Or
Oh yeah, sorry. Yeah, so it will be.
no homomorphisms?
It will be everything, but more emphasis on the stuff from the midterm till now. But there were a few people for health reasons or something that couldn't write the midterm. So I have to give a comprehensive exam for those students, like to test everything. And so, yeah, it will be for the entire thing, but more emphasis. Also in this course, it's hard to like the latter stuff builds on the former stuff anyways. So you can't really cleanly separate them. Unlike there's some courses where like every lecture is like completely independent of every other lecture. So prepare for the whole thing. But yeah, you have a cheat sheet, all the same stuff that applies. Bring a pencil, all those things, same things apply. The slot is 3 hours. You can take the 3 hours if you want, but I'm not going to try and write an exam that's 3 hours. I'll try and write an exam that's maybe an hour and a half or 2 hours, kind of thing. So I don't think at the end of it you'll be scrambling to try and finish. But also never written a final exam for this course, so I can't promise that for sure. But yeah.
Today is the last test?
When's the last?
Today is the last test?
Yeah, today's the last. Yeah, so next week, that's true of every class, unless if you have a class on Monday or Friday, then you will have a class next week because of Easter. But yeah, for us, today, this is last class. Yeah.
Someone who took this as their first class of cryptography, what would you recommend to see next, just as an extra class? Because this is not really my background. I just took this.
I see.
It was enjoyable, actually.
Okay, cool. So you could do, well, it depends on why it's enjoyable. So if you like the crypto aspect, we have 2 crypto courses. So there's 6110, which is crypto, and then there's 6120, which is crypto protocols and network security. And if you liked it more because it was applicable to real life and like there's a lot of interest in industry about it and like that kind of aspect, then I'd recommend my blockchain course, because it's also a similar thing where it's crypto, but it's applied, and there's a lot of like industry interest in it and things like that.
You teach that.
I teach that course too, yeah. I'll teach it next year. I can't remember if it's fall or winter, but it'll be one of
Which
those.
course is that?
So it's 6615.
615.
6615,
6615.
yeah. Okay, was there a question? Another question? Let me change this. So I already forgot. 23rd? Okay, that's it. That's all I have. Any other final questions? Parting words? Okay, good. All right, thanks everyone, and I'll see you in the exam.